Hey guys! This is the first of two videos for section 16.3 on the fundamental theorem of line integrals. I've noted here FTLI is an abbreviation I'll be using for that. Hopefully if you're watching this video you've already taken a look at 16.2 on line integrals, because we do need to know what line integrals are for this section. This is going to be an alternate method for computing certain kinds of line integrals of vector fields. Okay, now the special case that we're going to be focusing on is the case where we're dealing with vector fields that are conservative. Recall that. What I mean by a conservative vector field is any vector field that looks like the gradient of some sort of scalar function. So if you have no clue what the heck I mean by that, basically we're looking at f being conservative. Okay, I'll go ahead and write this out. If we've got the case that this vector field f looks like the gradient of some sort of function here, for some scalar function f. And then if this happens, if we actually do have the case that this thing was a gradient, f looks like maybe an x partial comma a y partial if it's 2D, or an x partial comma a y partial comma a z partial if it's 3D. If f looks like that, in this case, what we're going to call f is, it's the potential function, okay, for big F. Okay, so f is a potential for this capital F with a hat on it. Now, in this case, we're dealing with these conservative vector fields. A question I'm going to go ahead and pose is, what if we take line integrals of these things, right? What happens if we take line integrals of these? Now, this isn't a question I'm asking just because, I think it's fun. You actually do have some applications of this in physics. If you're trying to compute work in a gravitational field or an electrostatic field, the vector fields representing those are conservative. So if you're taking line integrals through them to compute work done by one of those fields, this is a case that we could be interested in. Okay, so, well, if I want to set one of these things up, what I would be looking at is a line integral over some sort of curve of, if it's a conservative field, it looks like a gradient. And since that does give you a vector field, this is one of those .dr type integrals and not one of the .ds arc length ones. Okay, so if I was trying to compute one of these, and I'm trying to use my old methods, with just what we know how to do right now, if I'm using my old methods from section 16.2, what that would have me do is find a parameterization. Okay, now what I mean by finding a parameterization, that curve that you're integrating over C, well, you can represent that curve by some sort of vector function r of t on some sort of interval. This will parameterize that path, and to compute this integral you would have to fix three things. Okay, fix my bounds, fix my function, fix my differential. Now this guy would have to turn into using the bounds a, b. Here you would actually have to either be given this vector field outright, and then you could substitute in your parameterization, or you would have to take that gradient yourself and then substitute in your parameterization. Okay, so I'll go ahead and note to fix that, you would have to substitute in whatever the heck r of t is, and then to fix your differential, well, we usually replaced the differential with basically r prime of t dt. Okay, and then keep in mind this dot product is still here. Okay, so your gradient is a vector, this differential is a vector. You actually do have to take a dot product here to compute this thing out. Okay, so basically from this situation, once we've fixed all of that, you could take this dot product and then compute. Now if that was all that there was to it, this wouldn't get its whole section by itself. We could have just taken care of this with 16.2. Now, the catch is, and why this thing gets its own section, is rather than jumping through all of those hoops, rather than, having to derive something just to sub some stuff in and then integrate it again, why do I have to derive it just to integrate it again? The idea of this section, especially since we called it the fundamental theorem, if you remember your fundamental theorem of calculus, like way back in Calculus 1, kind of the idea of that guy was if you derive and then integrate something frequently, you kind of get the original function back. So wouldn't it be nice if we could just do something similar to that, right? So it would be really, really nice, to have an FTC-like theorem, right? So that we could work through that shortcut instead of having to jump through all of these hoops and do all of these computations that, in some sense, they kind of cancel each other out, right? Like, why derive just to anti-derive again? It'd be a lot easier if we had some sort of a shortcut. Now, so happens, we do have this section, because that is a thing. We do have a fundamental theorem of line integrals, and the fundamental theorem of line integrals goes as following. I'll assume that curve that we're integrating this, conservative vector field over, I'll have that curve is smooth, we've got a parameterization for it, and that the function, the potential function that you're working with, it's a differentiable function, thus you can take a gradient, and we'll also assume that gradient's continuous along this curve. If we get that all of those hypotheses check out, and chances are if I'm throwing you a problem in this class, probably they do, then we get this nice formula right here. Okay, so this guy right here, I'm going to box it because it's important. This is my fundamental theorem of line integrals. Now, this doesn't quite look exactly like what you saw as the fundamental theorem of calculus back in Calculus 1, but I'll highlight why we call it the fundamental theorem and why it is actually similar to that, that theorem that we gave you a long time ago. The reason is basically this. In a sense, this guy right here, this function is, kind of similar to a derivative. I'll put derivative in quotes. This is maybe not exactly what we're taking here, but it's pretty similar to a derivative of f. Okay, the scalar function f. You're taking all of your partials for this, fx, fy, if there is a z, fz. And what you do is, if you anti-derive, think about me saying that with finger quotes around it. If we do something similar to an antiderivative operation, you would get the function f back, just little f, by itself. And in Calculus 1, whenever you went to evaluate a definite integral, you would antiderive, and then you would plug in the endpoints for your interval. Well, if we antiderive, read that with finger quotes, if we were to think about antideriving this function to get a little f, and then we were to think about plugging in the endpoints, well, we don't have endpoints of an interval, we have endpoints of a curve to worry about. So what I'm really looking at here is this is going to be my ending point of this C curve. Okay, R of B, that's me plugging B, my end time for this parameterization, okay, is the ending point on the curve R of B. And then what I'm doing is I'm subtracting off my starting point of this curve, okay? So pretty close to what we did in Calculus 1, you antiderive in a way, and then you evaluate at the endpoints, okay? Now, a big question that I can go ahead and ask about this is, why the heck does this work in the first place? It sounds pretty hand-wavy here, right? I'm even putting, derivative in quotes because It's not exactly the derivative of f. We don't have a derivative of multivariable functions f. We have partials instead. Let me formalize this. Why the heck does this thing actually work the way that I say it does? Well, let's think about this, right? If I actually go to evaluate this, now I'll go ahead and make the assumption one way or the other that I'm working with, let's say, a 2-variable function here. So I'll go ahead and assume my 2D case. Just go ahead and note that it works similarly in my 3D case if I did need to do that. What I'm really looking at in my 2D case is this. What is my gradient? Well, the gradient is just a vector where it looks like you took both of your partials and you shoved them in a vector, right? Now, if I were to go ahead and evaluate this thing as a line integral, what I would have to do is this. We would have to fix my bounds, fix my function, and then fix my differential just, like we had mentioned before, right? So me going ahead and doing that, this means that, well, if I fix my bounds, I no longer integrate over C. I integrate over the interval for my parameterization. Okay, we'll assume that that's AB now. I have to fix my function. That means I have to substitute in my parameterization. So really, I've got fx with r plugged in, and then I've got fy also with r plugged in. Here, let me leave room for my t here. And then for this bit on the end, the dot dr, we've said that to fix that, you really need r prime of t times dt. Well, if you're looking at r of t being this parameterization here, well, r is usually some sort of function. You specify an x coordinate, you specify a y coordinate at a given location of t. Those are functions of t that we can then take single variable derivatives of. So I would expect to get something that looks a little bit like this guy, right? So again, my assumption is my r parameterization looks like an x of t, y of t function. I just had to derive that and slap a dt on the end. Now, for me to go ahead and compute this, you do have to take a dot product before you actually anti-derive this thing. So I'm going to go ahead and take that dot product, but I'm going to write it in slightly different notation when I take it, right? Notice this fx function, right? This is really a derivative of my function f with respect to x. I just have some t stuff subbed into it. So here I'll note that was a df dx, okay, that has this function substituted into it. Now this thing on the end here, this is an x prime of t. Actually, let me make sure that I got my my partials straight here. I'm using the wrong d for that guy, so this should be the curly one because that was a multivariable function. So df dx. And then what I'm multiplying it by in this dot product is a derivative of x with respect to t. And then for the second part of my dot product, kind of similarly, I've got a derivative of f with respect to y multiplied by a derivative of y with respect to t. Now, hopefully this looks at least a little familiar. We have seen this expression before back in the chain rule section, right? So this guy really looks like the expanded chain rule formula for what happened when I wanted to take a derivative of f with respect to t, right? So here, this is df dt right here, that I'm going to go ahead and actually, take an antiderivative of. And the idea there is once you actually antiderive this thing, what you should get is just your f function back, right? You know, you take a derivative of something and then you antiderive it, you should get the original function back. But notice I can't just say that we did that and we got f back. This is making the assumption that we were working with a version of f that had this parameterization plugged into it, right? You know, you would expect that this thing being a function of t to derive with respect to that variable, you know, you had to have it in form of t in the first place. Now, the only way to get that is if you had plugged your parameterization in. Now, once we had anti-derived there, you know, this guy really is straight up fundamental theorem of calculus from calculus 1. You know, antiderivatives and derivatives cancel each other out. Once you actually take that antiderivative, you just substitute in the bounds, and, you know, your upper bound has to go in first, and then you subtract off what happens when you plug in your lower bound. Okay, so it really is especially fitting that we call this the fundamental theorem of line integrals, because we actually are using the fundamental theorem of calculus from calculus 1 to prove this thing in the first place. Okay, now, if you don't necessarily care about the derivation, if you just want to get into the example and see why we would like to do it this way, or why it might be worthwhile to try using the fundamental theorem of line integrals, let's see if we can get this through in an example, right? I've got a parameterization for a curve. I've got an interval, and it looks like I maybe for whatever reason didn't copy this over entirely. We'll go ahead and throw that 2 in there. I think that was supposed to be there in the first place. I've got this parameterization of, that's where my 2 went. So we've got this parameterization of this curve on this interval, and I've got a line integral that I want to take of a gradient, right? So this is going to be a conservative vector field. It's explicitly written as a gradient. How do I evaluate this thing? Okay. Now, just to give you guys a little bit of a comparison here, I'm going to start us off with the old way to do this, right? The old way of doing this, first off, I'm going to figure out what the heck this potential function actually turns into when I take the gradient. That means that I do need to look at an x partial and a y partial for this function. Well, your fx and your fy for this function are going to turn into the following, right? Your derivative of f with respect to x is going to be y, and your derivative of f with respect to y is going to be x, because both these just look like you dropped the variable off and you kept the constant left behind. Now, for fixing this, I would have to worry about replacing my bounds, my function, and my differential. And, you know, if I wanted to go ahead and do that, you know, my bounds, we just steal whatever interval my parameterization used. So my bounds are now going to be 0 to pi over 2. If I want to fix my function, right? What I need to do is look at the parameterization that I gave, and anytime that I see x, I'm going to sub in my x coordinate. Okay, so I'm going to sub in e to the t squared cosine t for x, and then I'm going to substitute in t cubed plus 5 for y. Okay, so basically the new thing I'm integrating is going to be this guy times this guy. And then the final thing that I need to do is then fix my differential that goes on the end. Okay, the differential that goes on the end, you know, dr is really supposed to be the same thing as r prime of t dt. And r prime here, in that first component, it's going to call for me using product rule, right? So I'll get a 2t to the t squared cosine t plus, or actually minus an e to the t squared sine t. And then the next piece I'll have a 3t squared, you know, plus 0, okay? And then all of that, I'll slap dt on the end. Now, for me to actually rewrite this, this integral right here, this is going to turn into an integral from 0 to pi over 2. If I do the substitution like I had mentioned before, substitute in this t cubed plus 5 for y, and substitute in, the e to the t squared cosine t for x. This thing needs to be dotted with, I can already see I don't have the, space to write this thing out, but basically I just get to copy this above line over in this vector, okay, with this dt on the end. And hopefully it goes without actually writing that out all over again. That's gonna be a hot mess, and I really don't want to take that dot product and then actually have to find an antiderivative of it. It's going to be really messy, right? I have all this potential here for me having basically these spots where I have polynomials times exponential functions times trig functions, and I'm gonna have to antiderive that? No. So we really do not want to do it this way, okay? Please, 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 please don't try it this way. It's gonna be a mess. What I would want to do is, in this particular case, since I know I'm dealing with a conservative vector field, is try the fundamental theorem of line integrals instead, okay? Fundamental theorem of line integrals instead. Okay, so what I'm going to go ahead and do is I'm just going to copy this over here, and then we will start anew down below and pretend that none of that ever happened, right? Let's try this with my new method, right? New method. Let's do my fundamental theorem of line integrals. If I try it that way, right, what the fundamental theorem of line integrals says, and I'm just going to copy this over verbatim without actually doing any of the work for it yet. My fundamental theorem of line integrals says that if I'm integrating this conservative vector field, I can just look at my potential function and see what happened when I evaluated this thing at the endpoint and subtract off what happened when I evaluate this thing at the starting point. Now, I've given you all of these things, right? I have given you what f is, okay, it's right here. I've given you what r is, it's right here. And a and b, I've given you what those guys are. They're right here. They're on that interval, okay? So once you have a parameterization for your curve and you know what your potential function is, you have all the pieces to evaluate this, right? So I'm going to go ahead and break this down. If I want to figure out what my A and B are, well, my B is my end time here, so that's my pi over 2. My A is my start time here, so that's my 0. And now, at this point, I'm worried about what happens if I plug in r of pi over 2, and then what happens when I subtract off r of 0. Now, I'm going to break each of those down. If I plug in pi over 2 to r, this is e to the pi over 2 squared cosine pi over 2, and then pi over 2 cubed plus 5. And then I have to subtract off whatever happens when I plug in 0. Well, this is e to the 0 cosine 0 and 0 cubed plus 5, so just 5 over here. Let's actually think about what this stuff is that I'm plugging in, right? Now, if I clean all this up, comment number 1 that I'm going to go ahead and make here, what's cosine of pi over 2? That's 0. So this whole thing, that first coordinate, is just going to simplify to 0. Everything in it's being multiplied by 0. Over here, if I expand this out, I've got pi cubed over 8 plus 5. And then I have to worry about, simplifying the rest of this. Both e to the 0 and cosine of 0, those come out to 1. So now what I need to worry about simplifying is what happens when I plug these coordinates into my f function. Now, f, in this particular case, was just what happens when I multiply my x and y components. So if I substitute these in, x times y in this first case is 0 times this other junk, okay? Honestly, I shouldn't even write it out because we already know that's going to drop off. And then I get to subtract off what happens when I take 1 times 5. So ultimately this thing comes out to minus 5. Notice, no nasty derivatives in this particular case, like we had last time. I'm not dealing with this like polynomial times trig times exponential antiderivative that I need to, none of that, right? So fundamental theorem of line integrals in this particular case, if you know that you are integrating something that's conservative, and you can figure out what the potential function is for it, in this case it was given, all you need to be able to do is plug in an endpoint and then subtract off whatever your starting point is. Okay? Now, some notes on this. Okay? Notes that I should point out. First off, and we've kind of seen this, given a parameterization for the curve that you're integrating over, if you've got this potential that you've taken a gradient of, or if you have this conservative vector field, all that the fundamental theorem of line integrals says is that when you look at that potential function, all you have to do is plug in the endpoints and subtract. That's it. Okay, so take your potential function, take the difference of what happens when you plug in the endpoints. Now this means the rest of the curve doesn't freaking matter in a conservative field, right? So if you pick 2 points in space, there's any of a number of ways that you could join those 2 points. Maybe I had a line segment, maybe I had an arc of a circle, maybe I had like some chunk of a parabola between them, maybe I had some other squiggly line. It doesn't matter if you're in a conservative vector field. So a comment that I'll go ahead and make about that, integrals like this, they have a special descriptor for them. Integrals like this are called path independent or independent of path. Okay, either way. So let me not be dyslexic here. Independent of path. Okay, so that is a comment that I'm going to go ahead and make about these integrals. If these guys are independent of path, rest of the curve really, truly does not matter at all. What that means is that, regardless of the path that you pick, okay, so regardless of your path from point A to point B, the result of your integral is going to be the same. Okay? And in fact, if you know the starting and ending points, you maybe don't even necessarily need to specify a curve, right? So an example here, suppose that my C is this line segment going from 0 pi over 4 2 to 1 pi minus 3. I could sit here, I could parameterize this thing. If you want to go ahead and pick some sort of a parameterization for this, you could, or we can be a little bit sneaky about this here, right? Instead of, finding your R of t and your AB for this parameterization, what I'm going to go ahead and note is the following, right? If I say R of B, I really mean my end point of this curve, right? Any line segment that we would have come up with, hopefully you plug in the end portion of your interval and you get 1 pi minus 3. Now, on a similar note, if I say r of a here, okay, as far as the fundamental theorem of line integrals is concerned, if I say r of a, what I'm really going to need is whatever the starting point of my curve is. So I can be sneaky and not even bother to find a parameterization, since I know that the thing that I'm integrating over is conservative, right? So if I go to set up my fundamental theorem of line integrals here, right? My fundamental theorem of line integrals, and I'm just writing the formula over right now. It says that you get to take f of r of b and then subtract off f of r of a. Now, when we go to set this up, before, I gave you explicitly a parameterization and an interval. Here you could find that if you wanted to, or we could go ahead and make this observation that this is just f of end minus f of start. So I'm not even going to bother, right? I'll go ahead and use the fact that we know that we're supposed to end at 1 pi minus 3, and we were supposed to have started at 0 pi over 4, 2. Now, those were supposed to be, substituted into this function that I gave you for f. I'm going to go back here and give myself a little extra room. This first point, I've got 1 plus minus 3 squared cosine pi. And then I'm subtracting off what happens when I substitute in 0 pi over 4, 2 to that same function. So 0 plus 2 squared cosine pi over 4. And then the rest of this is really just going to be, algebra, right? So 1 plus 9 cosine of pi is minus 1. I'm subtracting off 4 times root 2 over 2. Ultimately, I'm going to get minus 8 minus 2 root 2 here, okay? And notice we actually didn't find a parameterization because knowing that we were integrating something which was supposed to be conservative things are path independent, right? If these guys are independent of path, the path actually doesn't matter. You don't have to find the parameterization necessarily. You just need to know where you start and end. Now, a comment for the homework, if you're dealing with a path-independent integral, right? If you have some sort of path-independent integral, you really need to know this information on your endpoints. Okay, your information on evaluation of endpoints. And here I'm giving you guys actual algebraic functions that we can plug stuff into and get stuff back. I'm going to go ahead and note that this information can come in different forms. It can come from a graph. It can come from a table. It can come from an actual algebraically specified, let me spell that correctly, algebraic function. There's a bunch of different ways I could specify what happens when you plug a point into f. Be on the lookout for that, okay? So, I might be able to, specify, at 1 pi minus 3, this is what happens on this table or on this graph. We're not necessarily always going to be constrained to dealing with algebraic functions. Okay? Another comment that I wanted to make, since I am mentioning this bit about us having stuff that's independent of path, I don't want to completely throw out the idea of this curve. You'll notice that in all of these examples I've specified there's an ending point and a starting point, So the direction that we're traveling along that curve is actually kind of important, right? So I'm going to go ahead and note that since what we want, right, since we're looking at f of basically end minus f of start, if you swap the order of where you start and end, you're going to get a sign error, right? So I'm going to point that out right now. Swapping these, that's going to give you a big old sign error. So don't do that. Make sure that whenever you're traveling along a curve, you know where you're starting and you know where you're finishing, right? Now, what I have right here is this example where I'm supposing that we've got this line segment from 1 pi minus 3 to 0 pi over 4, 2. And I'm asking for you guys to evaluate this function, yada yada. Hopefully this looks familiar. And the reason that I say that is this. Let's go ahead and look at the last example that I gave you guys. It's the same function, right? So this thing right here is the same guy and the same points, but you'll notice that when I look at the points here, we're doing them backwards, right? So, you know, in this last example, I'm going to go ahead and note, this is basically my same f as last time, but that means that my end and my start points are swapped. Now, what did I just say happens when we know that that's the case? Well, you're going to get exactly the negative answer from last time, okay? So the negative result of what we got last time. And just for reference sake, I'm going to go ahead and flip back to the last slide and pull that up. You know, we boiled this down to minus 8 minus 2 root 2. Well, that means this is going to be 8 plus 2 root 2. I'm not even going to worry about redoing all of the algebra all over again, okay? I know I get a sign error by swapping the order. Just make my old result negative, okay? Another comment about traveling curves, you know, here I've noted what happens if we change direction. Another comment I can go ahead and make is, what happens if we're traveling along a closed curve? Now, what I mean by closed curve is this. If you've never heard the expression closed curve before, this is what it means. A closed curve is a curve that starts and ends at the same point. So basically what's going to happen is if you start right here and you travel along your curve, you know, maybe it meanders a little bit, maybe it crosses itself, whatever, it ends at the same point, right? Now, if you're starting and ending at the same location, think about what happens here. If I've got this, you know, f of end minus f of start idea for applying the fundamental theorem of line integrals to this gradient of f, well, basically the end point and the start point are the same thing, right? So it really looks like I've got f end minus f end because these are the same freaking point. And then if you subtract those off, you're getting 0, okay? So anytime that you're dealing with a C, you know, a curve that's closed, your fundamental theorem of line integrals is basically going to boil down to you getting a big old 0 back, okay? Now hopefully, if we think about one of the applications that I've raised before, this kind of makes sense from a physics perspective, right? I've mentioned that one of the applications that we use these line integrals of vector fields over is to compute work that could be done in a vector field. And, you know, if you remember, like way back in, you know, kind of like the baby version of physics, if you're dealing with, you know, constant forces, linear distances, anytime that you tried to compute work on an object that didn't freaking go anywhere, regardless of whether, you pushed it away and then you brought it back, if the starting and end position were the same, they assume that you didn't do any work. It's pretty much the same exact thing here, right? So if we're kind of shoving this thing all along this line, but you end up in the same position, net result, no work done. Okay, so hopefully this result kind of makes sense. Now, with that said, there are some theoretical consequences that I should just kind of get out of the way here, like us being independent of path. If we're independent of path on some sort of set D, that's going to imply that your integral of your vector field is going to come out to 0 for every single one of the paths that you could potentially traverse on D that's closed. And this if and only if statement here, I'll go ahead and make note of that for people that maybe aren't familiar with the mathematical notation. What this means, okay, is if and only if. And what I mean by that is that whatever this implication is bidirectional. Now, to translate that, if I could spell correctly, I don't know why I can't spell today, bidirectional. That also means that the implication works the other way around. So if you start out knowing that you've got this integral coming out to 0 for all of the closed paths on a set, that means that you also know that this is independent of path. Now, the idea for that is basically this. I'm going to go ahead and spell this out. Let's say that I know that something is independent of path. Okay, this vector is going to be independent of path on D, right? So I will start out with that implication. Now, if that guy is independent of path, that means that if I give you guys, 2 points in space here, and I pick different paths to travel to get from point A to point B, let's say I separate them, C1, C2, what this is going to imply, or actually be an equivalent statement to, is that in this picture here that I've drawn, I would expect that my integral for this thing over C1, this should come out to the same exact thing as my integral for this thing for C2. I get the same result if it's independent of path. We just said path doesn't matter, just the endpoints do. Now, a comment, if I just algebraically manipulate this, let's say that I subtract everything over to one side of the equation here, what that's going to suggest is that I'm going to get a big old 0 back, right? I'm going to scratch this out here. I meant for that to be an implication statement. I'm going to get 0 back, okay, for this integral. And then if I wanted to write a shorthand for this left-hand side here, another way that I could think about that is writing it in this manner. Now, this is a weird sort of expression because, maybe you're thinking, what the hell does it mean for me to be subtracting curves? Well, what I mean by subtracting these curves off is when I say this minus C2, think about traveling C2 backwards, right? We've said whenever we do things backwards, it induces a sign error. So what I'll think about is if I say minus C2, I really want to travel this way, right? So this thing is minus C2. And you'll notice that if I say that that thing comes out to 0, well, we've basically got some sort of closed path here that we just integrated over that's coming out to 0. Because if you traverse C1 and then C2 in the wrong direction, you're just following this thing in a loop. Okay, so this is kind of why this theorem works. If you're saying independent of path, we're basically getting, your integrals along closed paths are all 0. And then a final comment that I'll make to this as far as our theoretical stuff, I keep mentioning conservative, independent of path. We keep sort of seeing that these sort of mean the same thing, or at least we use these in very similar situations. There's a very, very tiny distinction here that's happening in which, I'm calling some things conservative and some things independent of path. They really pop up in similar cases. It's just that when I say conservative, that's a word that we use to describe vector fields, not integrals, vector fields. And when I say that something is independent of path, I'm referring to an integral. Okay? Now, granted, we are taking that integral of a vector field, but this is kind of the main distinction that we're using here, right? So I'll go ahead and kind of end us with this theorem and this example here. If you've got a vector field, that's, once you integrate it, it's independent of path. Your vector field that you integrated, that thing's going to be conservative. Okay, and we've already sort of seen before, if you have a conservative vector field, pretty much by definition, by the fundamental theorem of line integrals, it will yield a path-independent integral. So basically, for our purposes, think about these as referring to the same situation. It's just, are we talking about the integral? Are we talking about the vector field? Right? So I'll go ahead and give us an example where I have a conservative vector field that I'm integrating, because I am integrating a gradient. Let's go ahead and, look at this integral where I've got this curve C, that's the unit circle, centered at the origin, traverse counterclockwise from 1, 0. So I'm being very specific about my path here. Looks like that guy. Okay, travel in this direction. Now, what we just said is that this thing here, this is going to be a path-independent integral because this gradient thing, this guy is conservative, right? And since it's path-independent, and we are starting and ending at the same location, my integral has to come out to 0, right? So since this thing is path independent, if we are path independent on a closed curve, you're going to get that the result is 0. I don't even really have to do any work here. If you did want to, worry about, f end minus f start here, basically what I'm saying is this. We decided to end and start at the point 1, 0, so this is f of 1, 0 minus f of 1, 0. It's just going to come out to 0, right? We can save ourselves, even writing out the fundamental theorem of line integrals, we can definitely save ourselves writing out a parameterization for this curve and worrying about getting it facing the right direction, having it being the right radius and all of that. If it's path independent, save yourself the work. We're going to get something that comes out to 0 on a closed curve.